Noche cósmica.
There exists, somewhere above the curve of the Earth right now, a galaxy so distant that its light has traveled for 2.25 million years to reach your eyes. It is falling toward us, not tomorrow, not next month, but falling nonetheless, drawn by the invisible geometry of gravity across the vast dark. And somewhere in the quiet hours between dusk and dawn, if you find yourself beneath a clear sky, you might catch the faintest trace of it, a smudge, barely distinguishable from cloud, sitting in the northern autumn heavens. Imagine you are standing in a place where the modern world has loosened its grip, perhaps on a hillside far from the glare of cities, or in a meadow where the grass has grown tall enough to muffle the ordinary sounds. Above you, the sky opens like a book written in light. Your eyes, adjusting slowly to the dark, begin to discern what they have been missing all along. A vast river of stars, a pale luminous band stretching from horizon to horizon, flowing across the dome of night like milk spilled across black velvet. This is the Milky Way as our ancestors knew it, not as a concept or a photograph, but as an overwhelming presence, a lived experience of scale. Most of us have forgotten what this looks like. We live beneath the orange glow of street lamps and the scattered light of countless screens, and the Milky Way has become something we read about rather than witness. But on nights when you drift far enough from the noise, it returns, this ancient companion, this reminder that we inhabit not a world, but a galaxy. One among billions. Now, turn your gaze slowly toward the north, toward the constellation Andromeda. At first, there is nothing but darkness, a void between the brighter stars. But wait. Let your eyes settle. Let them gather the faint photons that have journeyed from so far away. There. A soft oval of light begins to emerge, elongated and diffuse, so faint that looking directly at it sometimes makes it disappear. This pale glow, this is not a single star, and it is not a cloud of gas within our own galaxy. This is another island universe entirely. This is Andromeda, and it is moving toward us. For millions of years, astronomers did not understand what they were seeing when they gazed upon Andromeda. They assumed it was a nebula, a cloud of dust and gas swirling somewhere within the Milky Way itself. The universe, they thought, contained only one galaxy. Everything was us. And then, in the early decades of the 20th century, a small group of scientists began to suspect something far more extraordinary, that this smudge on the sky might be a universe unto itself, as vast and complex as our own, separated from us by a distance so enormous that even light required millions of years to cross it. The idea seemed almost mad, but it was true. If you are curious about what happens when two island universes collide, if you wonder about the cascade of events that such a collision would set in motion, if you want to drift through slow, grounded journeys into the science and mystery of our cosmos, consider subscribing for more explorations like this one, where we examine the true fate of galaxies and the deep time in which their stories unfold. Returning to our imagined night sky, it helps to understand the true nature of what you are observing. The Milky Way in which we live is itself a vast spiral of stars, perhaps 150 billion of them, arranged in great sweeping arms that turn like the blades of a cosmic pinwheel. We occupy a modest position within this arrangement, not at the center, but somewhere in the suburbs, if you will, on a spur of one of the outer spiral arms. Our sun orbits the galactic center once every 230 million years, a leisurely journey of almost unimaginable duration. And somewhere within the crowd of stars surrounding us, invisible to our eyes but ever present, lies our solar system, our small corner of an enormous island. But Andromeda is larger still. Astronomers now understand that our neighboring galaxy is actually somewhat more massive than the Milky Way, possessing perhaps 2 trillion stars compared to our estimated 150 billion. It looms in the sky, not because it is close, but because it is so tremendously vast. 2 million light-years away, yes, but so enormous that even at that distance, its light spreads across a patch of sky wider than the moon itself, though so diffuse that most human eyes cannot see it without the aid of darkness and time. For a very long time, no one knew that Andromeda was moving toward us at all. The universe seemed static, eternal, unchanging. But in the early 1900s, a gifted astronomer named Vesto Slipher began studying the light arriving from Andromeda. He passed it through a prism, breaking it into its component colors, its spectrum, and there, in the displacement of those spectral lines, he found something extraordinary, a blue shift. The light was shifted slightly toward the blue end of the spectrum, the signature of an object racing toward the observer. Andromeda was coming closer. Decades later, Edwin Hubble would use new telescopes and new techniques to measure the distance to Andromeda with greater precision than anyone before him. And then, many more decades after that, the Hubble Space Telescope itself, named for Edwin Hubble, orbiting high above the Earth in the silence of space, would confirm with remarkable accuracy just how quickly our galactic neighbor is approaching. The measurements are refined still, but the truth remains. In about 4 billion years, Andromeda will collide with the Milky Way. But what if, as an exercise of imagination grounded in science, we were to compress that timeline into a single night? What if, instead of billions of years passing, the collision were to begin tomorrow evening, as the sun dipped below the horizon and the first stars emerged? This is not a prediction. This is not something we expect to witness. But it is a useful thought experiment, a way of understanding the profound and largely invisible processes that shape galaxies and determine their fates. To explore such a scenario requires first understanding a truth that might surprise you. The universe, on the largest scales, is almost entirely empty. 2 galaxies, despite seeming so solid, so densely packed with stars, contain so much void within them that a collision between galaxies is almost never, in the literal sense, a collision at all. Now imagine, if only in the theatre of your mind, that this distant rendezvous happened not billions of years hence, but tonight. Tomorrow morning, you woke to find Andromeda no longer a faint smudge requiring binoculars and a dark sky, but a presence, a growing presence. What would unfold in those first hours and days if the universe suddenly compressed 4 billion years of celestial patience into a single, accelerated night? This is a thought experiment, of course, pure imagination, though grounded in what we understand about gravity, motion, and the structure of galaxies themselves. A way to make the invisible visible, to feel the scale of forces that shape the cosmos even though we exist in the merest blink of its existence. The actual collision won't happen for billions of years yet, but let us pretend, just for a moment, that it could. When astronomers speak of a galactic collision, they mean something quite different from what the word might conjure in an earthbound mind. Not an explosion of impact, not a violent shattering, but rather a slow gravitational waltz. 2 vast islands of stars, each containing hundreds of billions of suns, beginning to feel the gentle, inexorable pull of each other's mass, drawing closer, warping, beginning to intertwine. But in our hypothetical tomorrow, this process would unfold not across the slow span of millions of years, but compressed into days and weeks and months. What normally happens at the speed of continental drift would accelerate to something almost we could perceive, frame by frame. The night sky above Earth would transform in ways that would reshape human understanding forever. Here is what makes this thought experiment so haunting. We would not be destroyed by it. neither would most of the stars in either galaxy. Instead, we would witness something far stranger. We would watch two entire universes of light begin to dance around each other, to stretch and contort and blend, while we ourselves remained almost entirely untouched. A cosmic performance happening at our doorstep while we stood, impossibly small, in the audience. This is the paradox of galactic collision. The universe is so profoundly empty, so vast in its distances, that even when two galaxies embrace, the stars within them almost never touch. Stars are not distributed like grains of sand on a shore, packed close and dense. They are scattered through space so thinly, so improbably far apart, that you could fit entire solar systems into the gaps between them and still have room left over. The Milky Way alone is roughly 100,000 light-years across, yet contains fewer stars than Earth has grains of sand. When you divide those numbers, when you truly contemplate the space between things, collision seems almost impossible. Yet collision of a sort would happen, not between stars, but between the galaxies themselves as unified structures. Their immense gravitational fields would interact long before any physical contact. Tidal forces, the same gentle effects that pull at Earth's oceans from the Moon's distant presence, would stretch both galaxies, pull them apart into long streams and bridges of stars and gas. The spiral arms would begin to warp and bulge. The shape that has taken billions of years to craft would start to unmake itself. And as those gas clouds compressed, as the shock waves of gravitational disturbance rippled through vast regions of hydrogen and helium, something beautiful would happen. Star formation would ignite. New suns would be born in vast numbers, kindled not by ancient processes, but by the violent, sudden awakening of the encounter. The disrupted galaxies would light up with newborn furnaces, casting off a brief and brilliant brightness as millions of stellar nurseries flared into life. The question that emerges, in this imagined midnight hour, is not whether we would survive. Most of us would. The question is what we would see, and what that sight would mean to us. There's something profoundly settling about learning how the universe actually works, isn't there? Not the sensationalized version you might glimpse on a hasty scroll, but the real story, told slowly, with the kind of patience that mirrors the cosmos itself. The kind of story that unfolds like a long breath on a quiet night. If you've found yourself drawn into this thought experiment, into the slow unwinding of what galaxies truly are and what they might do, then perhaps there are more journeys like this one waiting for you. More nights when you might lie in the dark and wonder about the deep mechanisms that hold our world in place, about the invisible architecture that keeps us tethered to this particular moment in time. We spend so much of our waking hours rushing from one urgent thing to another, rarely pausing to consider the gentler questions, the ones that don't demand answers so much as invite contemplation. What would you see if you could watch a star system form? How did astronomers first come to understand that the universe contained not just our galaxy, but countless others? Why does the void between galaxies feel so precious once you truly understand its vastness? These are the kinds of questions that might guide you toward deeper rest, if you give them the time they deserve. If you'd like to join us for more slow, science-grounded journeys through the cosmos, nights where we drift through the mechanics of black holes, or trace the history of how we came to know what we know about the stars, or explore the strange physics of time and gravity and light, we'd welcome you along. Each of these stories is written with the same unhurried rhythm, the same commitment to accuracy wrapped in narrative warmth, the same respect for your time and for the quiet hours you set aside to listen, the kind of companion you might return to again and again, whenever the world feels too loud and you need to remember how vast it is, how peaceful, and how much there is still to discover. For now, though, let yourself return to the sky above, to the thought of Andromeda drifting through the dark, and to the question we started with: what would truly happen if tomorrow night, instead of billions of years from now, the collision began. Our galaxy, the one that holds us, is a structure of remarkable grace and proportion. Imagine, if you will, a disk of light spanning 100,000 light-years from edge to edge. That is the Milky Way. Not a sphere, not a cloud, but a carefully organized spiral, with arms that sweep outward from a dense central core, like the unfurling petals of some vast and ancient flower, frozen in slow rotation. These spiral arms are not solid things. They are density waves, regions where the dust and gas and stars crowd together just slightly more densely than the spaces between them. The stars themselves, billions and billions of them, orbit at their own individual speeds, each one following its own elliptical path around the galactic center. The arms themselves rotate as a pattern, a ghost of structure that persists even as the stars within it slowly trade places, moving inward and outward like swimmers in a current. This has been understood only in the last few decades, a realization that humbled astronomers who had imagined the arms as material structures, permanent and fixed. The center of this spiral, that dense core we speak of, holds something extraordinary. At the very heart lies a supermassive black hole, something that astronomers have confirmed only in recent years through careful observation of stellar orbits. It is called Sagittarius A, and it weighs as much as 4 million suns. Around it, the stars move in their closest, fastest orbits, creating a gravitational anchor that holds the entire galactic structure together. Yet even this tremendous mass, inconceivable in its scale, exerts its gravity across a surprisingly intimate distance. The black hole itself is small, smaller than Mercury's orbit around our Sun, yet its influence extends throughout the disk, the halo, the very substance of what makes the Milky Way cohere as a single system. And where, in all of this, are we? We live in a suburb, not a fashionable one, not a quiet leafy one, but something more like the industrial outskirts of a grand city, far from the glittering downtown core. Our Sun orbits at a distance of about 26,000 light-years from Sagittarius A. We are tucked into one of the spiral arms, the Orion arm some call it, or the Orion spur, a minor branch that curls away from two of the Milky Way's major spirals, the Perseus and Sagittarius arms. Here, in this quiet neighborhood of the galaxy, we are so removed from the galactic center that the light pollution from the core barely reaches us. The density of stars around us is far less than in those crowded inner regions. We see the Milky Way as a pale band across our night sky, but we do not dwell in its brightest regions. We are observers, in a sense, of the outer suburbs of our own home. This is, in many ways, fortunate. The galactic center is a violent place, a region where radiation and cosmic rays and the close approaches of stars create an environment that would render life as we know it impossible. We exist instead in a region of relative calm, where stars are sufficiently separated that our Sun has never been battered by a stellar close encounter. We circle our galactic core once every 230 million years or so. That is the galactic year, the time it takes us to complete a single orbit at our current velocity. In the time since multicellular life first appeared on Earth, our solar system has completed less than a single lap around the Milky Way. We are ancient in human terms, yet mere children in cosmic ones. The structure we inhabit is also embedded within a larger halo of dark matter, an invisible cocoon of material that extends far beyond the visible disk of stars and gas. This dark matter has never been directly detected, yet its gravitational influence is unmistakable. Without it, the outer stars of the galaxy would be traveling too quickly to remain bound by the gravity of the visible mass. They would fly away. The fact that they do not suggests that the Milky Way is wrapped in this envelope of unseen material, making it far more massive than its light alone would suggest. It is a humbling reminder that what we see of our galaxy is merely the bright fraction of a much grander whole. So here we sit, in the suburbs of a spiral galaxy, on a small rocky world around an ordinary yellow star, itself unremarkable among hundreds of billions of its peers. The Milky Way spins around us, slowly, majestically, turning its arms like a cosmic wheel through the darkness. We are held in place by gravity, by the mutual attraction of matter and the geometry of space-time itself. We are home, and yet we are also part of something vastly larger than ourselves. This is the stage upon which our thought experiment unfolds. If you turned your gaze upward on a clear autumn night, away from the sodium lights of the city, you might catch sight of something that has haunted and delighted astronomers for centuries, a faint, elongated smudge of light in the constellation Andromeda, rising in the northeast. Most observers mistake it for a nebula, a nearby cloud of gas and dust stirred within our own Milky Way. But this is something far grander, far more lonely, and far more consequential to our imagined tomorrow. This is the Andromeda Galaxy, our nearest galactic neighbor, an island universe unto itself, separated from us not by the span of light years, but by something almost too large for the human mind to hold, the void of intergalactic space. Andromeda contains roughly 1 trillion stars. Let that settle for a moment. 1 trillion. If you spent 1 second on each star, naming it, cataloguing it, acknowledging its existence, you would need 32,000 years. And yet from Earth, this entire universe of stars, this civilization of light compressed across 200,000 light-years of space, appears to our naked eye as little more than a fuzzy oval. It is one of the largest and most massive galaxies in the local group, the loose federation of galaxies gravitationally bound to the Milky Way's own pull. In terms of sheer stellar content, Andromeda may even dwarf our home galaxy, though this remains a subject of gentle debate among cosmologists, who measure and remeasure, always seeking precision in the darkness. The distance between us is approximately 2.5 million light-years. 2.5 million. A light-year is the distance that light itself travels in 1 year, moving at 186,000 miles per second, and yet light from Andromeda takes 2.5 million years to reach your eye. The photons entering your pupil as you gaze upward tonight may have begun their journey during the early Pleistocene epoch on Earth, when the first stone tools were being shaped by human hands, when the climate was warm and strange, when our ancestors were still learning what it meant to walk upright beneath a sky they could not yet understand. And yet, despite this immense gulf, Andromeda is approaching us, not at the leisurely pace of orbital mechanics, but with the steady, inexorable momentum of gravitational attraction. It drifts toward the Milky Way at a velocity of approximately 110 kilometers per second, drawn by the gravitational embrace of our galaxy's mass, while we in turn are drawn toward it. 2 worlds, 2 islands in a cosmic ocean, locked in a slow dance that will eventually conclude in merger and transformation. The discovery of this approach, and indeed the discovery that Andromeda was a separate galaxy at all, is a story that belongs to the early 20th century, to a time when the universe was thought to be much smaller, when many astronomers believed that the Milky Way constituted the entire cosmos, and that nothing lay beyond its borders but emptiness and darkness. There was a man named Vesto Slipher, working at the Lowell Observatory in Arizona, who possessed the intuition and the technical skill to measure what others had only glimpsed. Using a spectrograph, an instrument that breaks light into its constituent wavelengths, he observed the light from Andromeda and noticed something peculiar. The spectral lines, those dark or bright bands that reveal the composition and motion of distant light sources, were shifted toward the blue end of the spectrum. This shift toward blue light indicated something moving toward the observer, an effect discovered decades earlier by Christian Doppler when he noted that a sound source approaches with a higher pitch and retreats with a lower one. Light behaves in the same way. In the 1910s, when Slipher made these observations, the prevailing assumption was that Andromeda was a nebula within our own galaxy, and its approach seemed to contradict the otherwise universal expansion of the cosmos that had begun to emerge as a possibility in theoretical physics. Yet Slipher continued to observe, and he continued to measure, and gradually the evidence accumulated. It would take another astronomer, Edwin Hubble, working with what was then the largest telescope in the world on Mount Wilson in California, to provide the definitive proof. Hubble observed individual stars within Andromeda, identified certain types of variable stars whose true brightness could be calculated, and measured their distances. In doing so, he demonstrated conclusively that Andromeda lay far beyond the Milky Way, that it was indeed a separate galaxy, a separate island universe populated with billions upon billions of stars, and perhaps worlds beyond counting. The news of this discovery rippled through the astronomical community, like a pebble dropped in a still pond. The universe, overnight, became vastly larger and far less lonely. Decades later, when the Hubble Space Telescope was launched into orbit, when technology had advanced to the point where we could measure stellar motions with extraordinary precision, the measurements of Andromeda's approach were refined and confirmed. The blue shift that Slipher had first detected was not an artifact or an anomaly. Andromeda truly is moving toward us, drawn by the vast gravitational machinery that governs the cosmos. And in our thought experiment, in the compressed timeline we are exploring together in the darkness of this night, that slow approach culminates in something cataclysmic and beautiful. If we trace back to the earliest whispers of this cosmic knowledge, we find ourselves in the early 20th century, in a quiet observatory perched in Arizona, where a man named Vesto Slipher was peering through a spectroscope at what everyone then assumed was nothing more than a nebula, a cloudy smudge within our own Milky Way. Slipher, working methodically through the Arizona nights, noticed something remarkable when he split the light from the Andromeda Nebula into its component wavelengths. The light was shifted, blue, toward the blue end of the spectrum, which meant, in the language of light itself, that Andromeda was moving toward us. The whole structure was rushing inward through the void at something like 300 kilometers per second. It was 1912, and Slipher had discovered our cosmic neighbor was coming closer. Yet the full significance of what he had found would not become clear for many years, because the fundamental question of the universe itself remained unanswered. Was Andromeda truly another galaxy, another island of stars beyond our own, or was it simply part of our galactic system, a mere appendage to the Milky Way? The great debate of the era hinged on this very question, with astronomers divided into schools of thought, uncertain whether the universe contained one vast island or many. It would take a tall man with patient hands and an exceptional gift for observational precision to settle the matter. Edwin Hubble arrived at Mount Wilson Observatory in California with exactly those qualities, and in the mid-1920s, using the most powerful telescope of his time, he carefully resolved individual stars in the outer reaches of the Andromeda Nebula. These were stars, unmistakable Cepheid variables whose brightness pulsed with a rhythm that allowed him to measure their true distance. The numbers were staggering. Andromeda was not a nearby nebula within our galaxy. It was nearly 1 million light-years away, a separate universe unto itself, and the cosmos suddenly expanded in the minds of those who read his papers. Now we understand something crucial. The light that Vesto Slipher had measured, the blue shift, meant something different than merely approaching through empty space. Rather, it revealed that Andromeda retained some of the cosmic motion left over from the Big Bang itself, a subtle drift inward that has persisted through billions of years. The thought is almost meditative when you consider it. two galaxies born from the same inflationary moment, nudged slightly toward each other by the curvature of space-time, gradually winding down that ancient momentum. For decades after Hubble's confirmation, the trajectory of Andromeda remained difficult to measure with certainty. Astronomers could see that the blue shift existed, but the precision required to determine not just the speed of approach, but also the sideways motion, the tangential velocity, was beyond what any ground-based observatory could achieve. It was not until the Hubble Space Telescope, launched into orbit in 1990, and named for the very man who had confirmed Andromeda's nature decades earlier, that we could finally nail down the numbers with confidence. And the results, when they came, confirmed what Slipher had suggested and what more recent measurements had implied. Andromeda is definitely approaching. The two galaxies are bound to one another, caught in a gravitational embrace that will eventually draw them together. The measurements from the Hubble Space Telescope revealed something even more detailed, not merely the speed of approach, but the three-dimensional motion of Andromeda through space. By observing how stars within Andromeda shift their positions against the distant background of more remote galaxies, astronomers could construct a complete velocity profile. Andromeda moves toward us at about 110 kilometers per second, but it also has a sideways component, a lateral drift across the sky. These measurements, refined through careful study of stellar motions, gave us the collision course itself. The two galaxies are not heading directly for a head-on impact. The geometry is slightly offset, a glancing blow rather than a direct strike. And it is this lateral motion that means, when the galaxies do eventually merge, they will spiral around each other first, a waltz of gravity that will last for hundreds of millions of years. There is something profound about recognizing that the ancients who looked up at the smudge of Andromeda in their night skies could not have known they were looking at another island universe on a collision course with their own. Vesto Slipher, working by the light of a spectroscope in the Arizona darkness, could not have known that his blue shift would later confirm one of the great dramas of cosmic history. Even Edwin Hubble, peering through the eyepiece at Mount Wilson, seeing those distant Cepheid stars winking into visibility, could not have grasped the full weight of what his measurements meant for the future of our galaxy. The knowledge crept up gradually, built from careful observation and patient measurement. Each generation of instruments, and each refinement of technique, adding a little more clarity to the picture. When the Hubble Space Telescope finally provided those precise numbers in the 1990s and early 2000s, the scientific community could state with confidence that yes, the collision is real, it is inevitable, and it is inexorably approaching. Not tomorrow, not for billions of years yet, but there is a certainty to it now that was absent before. The blue shift that Slipher had seen, a subtle shift in the color of distant light, had been translated into a cosmic reckoning, and we, the inhabitants of a galaxy that has never experienced such a collision in all of its history, are the first generation to know it is coming. And here is where the true strangeness begins, because what we are about to describe will seem to contradict everything our minds expect. Two galaxies, each containing billions upon billions of stars, moving toward each other through the darkness. Surely, you might think, such a collision would be catastrophic beyond measure. Surely the heavens would crack and splinter. Surely stars would rain down like meteors across an endless night. But the universe has arranged things in a way that defies our intuition. Consider for a moment the actual distances involved. The Milky Way stretches roughly 100,000 light-years across. Within it, our Sun resides in the Orion Spur, about 26,000 light-years from the galactic center. That is an almost incomprehensible distance, yet it is merely one suburb within a single city of stars. And the stars themselves, between our Sun and its nearest stellar neighbor, Proxima Centauri, lies over 4 light-years of empty space. 4 light-years. That is enough room for trillions of kilometers of absolute, profound nothingness. Now think of this emptiness not as a flaw in the galaxy's architecture, but as its defining characteristic. A galaxy is not like a city of lights packed together on a plane. It is far, far more sparse. If you were to shrink the Milky Way down to the size of a large city and scale every distance proportionally, the sun would be a single grain of sand somewhere in the suburbs. The nearest other star would be another grain of sand several miles away. The rest would be empty desert. This is the secret that makes galactic collision possible without the catastrophe we imagine. Space, even within a galaxy, is almost entirely empty. When Andromeda passes through the Milky Way, or, in our thought experiment, arrives tomorrow, what would actually occur is something far gentler than a collision. It would be something more like two vast clouds of smoke passing through one another. The two galaxies would indeed disturb each other's structure. Their mutual gravity would pull at them, stretching them, warping their spiral arms into bridges and tails and streams of stars. But the probability of any individual star in one galaxy actually striking any individual star in the other is almost impossibly small. Do you understand how small? If we were to calculate the likelihood of our Sun, specifically, colliding with any single star in Andromeda during a galactic merger, the odds would be somewhere in the range of 1 in 1 billion billion, 1 in a billion billion. It is a number so remote that we might call it, for practical purposes, zero. And this is not pessimism or exaggeration. This is mathematics at the scale of the cosmos. Why is this so? Because even when two galaxies merge, they remain mostly empty. The stars within them are so far apart that they can move past one another like schools of fish in a vast, dark ocean. There is room to pass, always room to pass. The gravity that pulls the galaxies together does not pull the stars into collision. The gravity of the galaxies operates at a much larger scale, on the distribution of mass across the whole system, on the great rotating disks of hundreds of billions of objects. It is like watching two whirlpools begin to merge. The motion is dramatic, the shape changes, but an individual droplet of water in one whirlpool need never touch a droplet from the other. What does happen, instead, is that the gravitational fields of the two galaxies begin to deform each other long before any actual merger occurs. The tidal forces, the difference in gravitational pull across the extended disk of each galaxy, would begin stretching them. Stars on the near side of the Milky Way would feel a stronger pull toward Andromeda than stars on the far side. This difference in pull would not be uniform. It would create tidal forces much like the moon creates tides on Earth's oceans, but on a scale so vast that entire galactic disks would begin to warp and twist. The spiral arms would become distorted. Streams of stars and dust would begin to flow outward, pulled by gravity into long, delicate tendrils. These tidal tails are not rare phenomena. Astronomers have observed them throughout the universe. When two galaxies merge in the distant universe, we often see remnants of such tidal interactions, long, ghostly streams of stars extending away from the merged galaxy for hundreds of thousands of light years. These are the fingerprints of gravitational violence made visible. They are beautiful, in a way. They show us the power of gravity working on the grandest scales. But here is what is essential to understand. Even as these dramatic tidal forces reshape both galaxies, even as stars are pulled outward into streams and tendrils, even as the orderly spiral arms are twisted and torn apart, the probability of two stars actually colliding with one another remains vanishingly small. The emptiness is too great, the space is too vast. You might wonder then, what would actually happen to individual stars as this cosmic dance unfolded? Would they simply drift undisturbed, as if passing through a ghost? Would their paths be altered? The answer is that some stars would indeed be pulled into new orbits. their trajectories altered by the combined gravitational pull of both galaxies. But they would not collide. They would be redirected, perhaps, the way a small pebble might be altered in its course by the presence of a distant mountain. The probability remains vanishingly low that any star would find itself on a direct collision course with another. This is the paradox of galactic mergers. They are violent events in the sense that the structure of galaxies is fundamentally transformed. The shapes are destroyed and reformed. Stars are scattered across vaster orbital paths. The organized beauty of a spiral galaxy can become a chaotic mess of stars and dust and gas clouds tumbling through space. Yet at the same time, these events are gentle in another sense, because individual stars almost never actually touch. The cosmos has carved out its drama in the emptiness between things, not in the things themselves. Now, in this thought experiment of galaxies colliding tomorrow, there is something rather beautiful to contemplate about the nature of cosmic emptiness itself. You see, when two galaxies pass through one another, the thing that most people imagine, a catastrophic smashing of stars, a violent collision of burning suns, is almost certainly not what would happen. The reason lies in something almost impossible to grasp when you first encounter it. Space, even within a galaxy, is almost entirely empty. Think about the vast gulf between our Sun and its nearest stellar neighbor, Proxima Centauri, lying some 4.2 light-years distant. That is an almost incomprehensible stretch of vacuum, a journey that would take our fastest spacecraft over 80,000 years to complete. And now imagine that same kind of spacing repeated trillions upon trillions of times within the Milky Way itself. We are not living in a crowded cosmic city. We are living in a scattering of lanterns across an ocean of darkness so profound that even the closest lights feel impossibly far away. For two stars to actually collide, for their surfaces to touch, they would need to pass within perhaps 1 million miles of each other, a distance that sounds vast until you place it against the gulf between them. In the collision of two galaxies, even as they pass through one another and their stars fly among the stars of their neighbor, the probability of any two stars actually coming close enough to interact gravitationally in a dramatic way remains extraordinarily small. Astronomers have run the calculations many times, and the numbers consistently reveal the same thing. In a galactic merger, even one unfolding tomorrow, direct stellar collisions would be vanishingly rare, almost impossible. Consider the numbers at work. Our galaxy contains somewhere between 2 and 400 billion stars, perhaps more. Andromeda holds 1 trillion, or thereabouts. We are still refining our estimates. Those are numbers so large they lose meaning in the mind, and yet when you account for the volume of space that both galaxies occupy, the density of stars remains almost improbably low. Imagine scattering 400 billion grains of sand across an area the size of an entire continent, and then imagine a second continent's worth of sand spreading through the first. How many grains would actually touch? There is also the matter of time, which is perhaps the most crucial element in this calculation. Even in our compressed tomorrow scenario, even as the galaxies interpenetrate and pass through each other, the process would unfold not in minutes or hours, but over months and years. Stars do not move instantaneously through space. Even as gravitational forces tug them this way and that, they trace their paths with a leisurely, almost stately grace. A star passing near a star in the old systems of both galaxies would have weeks or months in which to be deflected by gravity, to miss its would-be collision partner by the thinnest of cosmic margins. What we should expect instead, and this is where the true drama of a galactic merger emerges, are encounters of a different sort entirely. Stars would pass near one another in gravitational close calls, their trajectories bent by the invisible pull of massive neighbors. These near misses, numerous though they might be, would send stars careening from their normal orbits. Stars currently moving in stately ellipses around the galactic core would be flung outward into strange new trajectories, or yanked inward toward regions of greater crowding and chaos. It is not collision in the violent sense, but rather a reshuffling of the cosmic deck, a rearrangement of orbits so profound that the entire architecture of both galaxies would be remade. Some stars would be ejected entirely from the merged system, thrown outward into the darkness between galaxies, becoming vagrant wanderers in the intergalactic void. Others would be drawn deeper into the central regions where gravity's pull grows more intense. A few might even be captured into tight binary orbits around stars from the neighboring galaxy, creating sudden pairs that would orbit each other for billions of years to come. It is a delicate dance, more often than not, rather than a crash. This is where the beauty of physics reveals itself in full measure. The same emptiness that would prevent direct stellar collisions is also what allows for this graceful, albeit violent-looking, rearrangement. The galaxies can interpenetrate. They can pass through each other with their forms visibly distorted, their spiral arms stretched and twisted into streams and bridges and tidal tails, while the vast majority of their stars remain unscathed by direct impact. It is a kind of cosmic choreography, a weaving together of billions of suns in patterns neither galaxy possessed before, and it arises not from stars smashing into stars, but from the patient, inexorable pull of gravity across unimaginable distances. Yet even as we frame this in mathematical terms and speak of probabilities and orbital mechanics, there remains something to keep in mind. In an actual galactic merger, tomorrow or 4 billion years hence, the fate of any individual star, including our own sun, hangs on conditions and chance events that are almost unknowable in advance. Computer simulations can give us broad outlines, can show us the likely overall shapes and transformations, but the specific trajectory of one particular star among hundreds of billions, its path shaped by the gravitational influence of thousands of its neighbors, remains beyond precise prediction. There is order in the chaos, mathematics in the motion, and yet also a kind of randomness that humbles even our most sophisticated calculations. But now we arrive at the heart of our thought experiment, and here is where we must gently lower the curtain between what astronomy can tell us with certainty and what we must imagine together in the dark. The question itself, what if Andromeda collided tomorrow, is not something that science can predict in literal detail, because the variables are almost infinite, and the timescale is absurd. 4 billion years from now, yes, astronomers can model with reasonable confidence what will unfold. The physics is understood, the initial conditions are measured, but compress that cosmic drama into a single night, and we step away from prediction and into the realm of pure thought. This is important to hold gently in your mind as we continue. Imagine then that tomorrow evening you step outside as you always do, and the night sky is still itself, the same constellations, the same faint smudge of Andromeda in the northeast where it has always been. The evening feels like any other. But let us pretend, for the sake of this journey, that something has accelerated in the depths of space. Something has compressed the future into the present. What would you witness? Not predictions, mind you, but the unfolding of principles we know to be true, collapsed into hours instead of eons. It is a kind of storytelling, but it is storytelling grounded in real physics, real measurements, real understanding of how galaxies behave when they draw near. In our scenario, as midnight approaches, you might notice something odd if you were watching carefully. The shape of Andromeda itself, that faint elongated smudge, would seem to shift. It would appear to swell, not suddenly, but perceptibly, as if something vast were rising over the horizon. And this is where the line between science and imagination blurs most delicately. We know that tidal forces would begin to deform both galaxies. We know this from theory and from observation of other merging systems seen through telescopes. But the exact dance, the precise choreography, the specific moment at which a human observer would first perceive it, these become shades of color painted on the canvas of what must remain, for now, unknown. The peculiar thing about collapsing time in thought is that it forces us to confront a fundamental question. What is visible to the human eye in the first place? Andromeda is so enormous, twice the width of the full moon as seen from Earth, yet it appears so faint because its light is spread across such a vast area. If the merger were happening at true cosmic speed, most of the visual drama would unfold not in hours, but in the faint whisper of photons arriving from ever-changing configurations of stars and gas. Your eye, adapted as it is to the night, would register something genuinely alien, but would it appear as a violent collision, as the word suggests? This is where we must be honest and say, probably not, not in the way human intuition might imagine it. Here is what we are confident about, even as we compress the timeline. The gravitational influence of one galaxy upon the other would be profound and immediate. The delicate architecture of each spiral arm, each trailing stream of ancient stars, would feel that pull like a harp string drawn taut. The mathematics tells us this, the computer models confirm it, but the subjective experience, what a human being standing on Earth would actually see, moment by moment, requires us to venture into speculation. We are no longer reporting, we are constructing a narrative from the blueprint of physics. This distinction matters because there is a temptation, when encountering the unknown, to either overstate it or diminish it, to either imagine the sky tearing open in Hollywood fire and brimstone, or to dismiss it as merely academic and therefore unimportant. Neither captures the truth. What we are doing instead is moving carefully into the space where science ends and the artist's eye takes over, not to invent falsehoods, but to arrange known truths in a way that honors both their precision and their mystery. For the purposes of our evening walk through this imagined tomorrow, we will move forward with this understanding. Everything we describe will rest on foundations of established astronomy, but the specific sensations, the exact visual progression, the moment-by-moment experience will be colored by educated imagination, by what we might reasonably expect, given what we know about gravity, matter, light, and time. We are building a thought experiment that is faithful to physics, even as it transcends prediction. Some listeners find this uncomfortable, others find it liberating. Perhaps you are among those who appreciate the precision of the boundary itself, the willingness to say, here is what we know with confidence, and here is where we must venture into the beautiful uncertainty of speculation. It is a more honest approach to the cosmos than pretending certainty where none exists, or insisting that only cold prediction has value. So let us take that step together now, understanding exactly what we are doing. We are not pretending that astronomers have hidden calculations predicting the precise minute-by-minute unfolding of tomorrow's collision. We are instead opening a door to imagination that is anchored to reality. We are asking, if the physics we understand were to play itself out at an impossible speed, on an impossible timescale, what would the principles themselves tell us about what might unfold? And in that gap between the knowable and the imaginable, we will spend our evening learning and wondering both. Imagine, then, the first hours of this imagined tomorrow. The evening sky darkens as it always does, stars emerging in their familiar patterns, the great wheel of the Milky Way rising overhead in its ancient arrangement. But within perhaps the first hour of true night, something unprecedented would begin. High overhead, where Andromeda has always been a faint, elongated cloud, visible only to those who knew where to look, a change would manifest so gradual at first that you might question whether your eyes were deceiving you. The smudge would be slightly brighter, just slightly, like a dimmed lamp someone had nudged just a fraction higher. By midnight, the difference would be undeniable. Andromeda would have swollen noticeably, its angular size increasing as it rushed through space toward us at roughly 110 kilometers per second, a velocity so immense that distance collapsed like folded paper. Where the galaxy had occupied perhaps 6 full moons worth of sky, it would now span 8, then 10. The growth would continue with an eerie, patient inevitability, as though some unseen hand were slowly pulling focus on a telescope's eyepiece, bringing the distant into terrible clarity. What would be most striking, perhaps, is not merely the swelling but the revelation of structure. For all of human history, Andromeda has appeared to observers as something nebulous, almost ethereal, a ghostly smudge that challenged the boundary between cloud and star. But as it approached, its spiral arms would begin to resolve. Where there had been a uniform glow, fractures of light would emerge. The great dust lanes that wind through Andromeda's disk, vast dark clouds of gas and stellar nurseries, would become visible to the naked eye, sketching shadow and illumination across the galaxy's face. It would look, for the first time, not like a vague luminous fog, but like what it truly is, an enormous pinwheel of 100 billion stars, a city of suns arranged in elegant, sweeping curves. The core of the galaxy would brighten dramatically. Andromeda's central bulge, already home to billions of ancient stars packed densely together, would burn with an intensity that would rival the brightest planets in our own sky. And at the very heart of that bulge, invisible but present, the supermassive black hole at Andromeda's center would wait, drawing closer with each passing hour, though it would take days or weeks before the true gravitational violence began in earnest. For now, it would merely pull, silently, inevitably. The color of Andromeda would shift as well, though subtly. The galaxy is not uniformly golden or blue, but a complex tapestry. The older stars, concentrated in the bulge and scattered throughout the spiral arms, would glow with reddish warmth. The younger stars, brilliant and massive, would shine with blue intensity, tracing the structure of the grand spiral design. As Andromeda's light grew stronger and reached Earth's surface with greater intensity, these colors would become more distinct, more vivid. Someone with even modest telescopic aid would begin to see the galaxy not as a two-dimensional apparition, but as a three-dimensional architecture, a true island universe with depth and structure and character. And perhaps most unsettling would be the speed of this change. To watch the night sky transform in a way that spans hours rather than years or millennia touches something primal in human perception. We are accustomed to the heavens being still, eternal, unchanging on any timescale that matters to us. The constellations our ancestors knew remain unchanged for us, and their descendants will see them largely the same. But here, in this thought experiment, that assumption would shatter. The permanent would reveal itself as temporary. The still would prove to be moving. Yet something important must be held in mind as we imagine this scenario. The collision itself would not feel violent at first, despite the spectacular light show. No one on Earth would feel trembling. No earthquakes would shake the ground. No sudden disturbances would announce the collision's beginning. The two galaxies are separated by incomprehensible emptiness. They are islands of matter, suspended in a vast ocean of nothing. As Andromeda approached, all the change would be astronomical, quite literally, in the truest sense of the word. It would be visible, it would be transformative to observe, but it would not immediately be felt. The swelling of Andromeda in the night sky would continue, day after day, if we were to follow this imagined scenario forward. Each night it would be noticeably larger than the night before. The spiral structure would continue to resolve. The dust lanes would grow more intricate and defined, and somewhere in the back of the human mind, watching this unfold, there would be the peculiar mix of wonder and vertigo that comes from witnessing the cosmos reveal its motion, its dynamism, its essential indifference to the small worlds that watch it spin. And as that pale disk swells across the black, something begins to happen that no telescope on Earth would ever show you in real time. Something that reaches across the void with an invisible hand. The galaxies, as they draw closer, begin to feel each other's weight in ways that reshape them entirely. This is the subtle, inexorable pull of tidal force, and it is perhaps the most haunting dance in all of astronomy. Imagine standing on a bridge between two mountains, each mountain exerting a different pull on your body, depending on which direction you lean. The gravity of one mountain tugs harder on your left side, the other on your right, and in that difference, in that gradient of gravitational pull, you begin to stretch. This is what happens to a galaxy when another galaxy approaches. The near side of our Milky Way, the side facing Andromeda, experiences a stronger tug than the far side, and in that asymmetry lies the seed of transformation. The outer stars, those ancient wanderers that orbit in the galactic halo, the faint, sparse sphere of older stars that surrounds our bright disk like a diffuse crown, begin to trail away first. They are the least tightly bound, the most vulnerable to the whisper of a rival galaxy's gravity. These stars, which have perhaps never strayed far from their birthplace in billions of years, are drawn outward in long, delicate streams. Picture them as they peel away, not violently torn, but gently coaxed, as if invisible threads are drawing them toward Andromeda, creating long filaments that arc across the darkness like the tentacles of some great cosmic squid made entirely of starlight. And as these outer streams extend, the spiral arms themselves begin to distort. The grand architecture that we know, those graceful curves traced by dust and young stars, warps and ripples. The arms that once were smooth curves become twisted, their geometry bent by forces working from all directions. Some regions stretch outward, others compress. It is like watching a whirlpool in reverse, not drawing inward but expanding, unraveling, yet paradoxically becoming more complex in the process. But it is not only the stars that feel this pull. The vast clouds of gas that drift between the stars, hydrogen and helium, carbon and nitrogen, the raw material from which future worlds are born, these clouds too begin to stream outward. And here something remarkable happens. As these clouds are drawn away from their home galaxy, some are compressed by the gravitational tides, squeezed and heated by the weight of nearby material. The gas heats, the gas begins to glow. In those compressed regions, new stars will ignite, brief nurseries of birth scattered through the disrupted galaxies like embers in ash. The dust, too, becomes visible in this choreography. Dust that ordinarily hides behind the visible light of stars, dust that blocks our view of the galactic core, is now pulled into trails and bridges. These dust streams cross the space between the two galaxies, faint at first, growing more substantial as more material is drawn outward. They form a kind of cosmic scaffold, visible in infrared light that a patient observer might detect. Bridges made of particles so fine that trillions could fit in the space of a grain of sand. What forms between the galaxies in this imagined scenario? And let us be gentle here and acknowledge that we are now deep in the realm of simulation, of computer models and extrapolation rather than direct observation, are structures that astronomers call tidal tails. These are streams of stars and gas that extend far into space, sometimes reaching for distances of hundreds of thousands of light years. They are not permanent. They do not hold together indefinitely, but in the moment of closest approach and in the years that follow, they are visible expressions of gravity itself, made manifest, the invisible field made briefly flesh, or rather, made briefly of light. Think of what is remarkable here, the gravity that binds a galaxy together. The same force that keeps you anchored to the Earth is strong enough to reach across the intergalactic void and visibly reshape a trillion stars. This is not a collision in any violent sense. There are no explosions. There is no impact. There is only the slow, patient geometry of curved space-time, the bend in space itself that mass creates, and the inevitable dance of objects following the contours of that bend. In some ways, it is the most elegant catastrophe possible, a transformation that is gentle in its operation, yet profound in its consequences. The bridges that form between the galaxies are gossamer thin by stellar standards, yet they contain enough mass to reshape the cosmos in a way that would be visible from planets light years away. If a world existed in the path of one of these tidal streams, the sky above it would gradually fill not with a collision's violence, but with the slow creep of new structures, new stars, new arrangements of light. And as these tidal forces work, as the streams extend further and further, something else becomes true. The galaxies are already losing the race against each other. Once set in motion by these forces, the material being drawn away will never return to its home galaxy. It will drift forever in space, a ghostly record of this encounter, visible to future astronomers as evidence that something profound once happened here. As the two great spirals draw into their dreadful embrace, something unexpected awakens in the darkness between them. The vast clouds of gas and dust that have drifted quietly for billions of years in the spaces between the stars find themselves caught in a squeeze they have never known. Where once there was only vast, cold emptiness, there is now compression, there is now pressure, and pressure, in the cosmos as in all things, has a tendency to ignite. Picture, if you will, the immense hydrogen clouds that float through the outer arms of our Milky Way, cool, diffuse, mostly inert. These are the nurseries where stars are born, but they are sleeping nurseries, where births come slowly, one or two bright infants every few millennia in any given region. But now, as Andromeda's gravity reaches across the interstellar dark and the tidal forces flex and bend the structure of both galaxies, these clouds begin to collide with one another. Not violently, not in the way a stone strikes stone, but with an inexorable, irresistible compression that forces their molecules closer and closer together. The density rises, the temperature climbs, and in that climbing warmth, in that gathering pressure, the secret of star formation waits. Within these newly compressed clouds, gravity itself becomes an accelerant. Where the gas thickens enough, atoms begin to cluster. A knot of hydrogen here, a denser pocket there. Each little region of extra concentration pulls harder on its surroundings, drawing more material inward, growing heavier, growing hotter, and then, quite suddenly, in pockets scattered throughout the disturbed spiral arms of both galaxies, a threshold is crossed. The core temperature of these collapsing clouds reaches something like 10 million degrees. Hydrogen atoms begin to fuse, light erupts, a star is born. But not just one star, thousands, tens of thousands, hundreds of thousands perhaps, igniting across the face of both galaxies almost in concert. The astronomers who have studied galaxies in collision, and there are real observations of this, real images from the deep universe showing galaxies in the very midst of their merger, they see this signature written plainly. A burst of brilliant blue light. New stars, hot and massive and short-lived, blazing across the dark like a fever breaking out across a sleeping body. The entire outer regions of both galaxies would begin to glow with this new, frantic activity. What was once a relatively quiet suburban arm of the Milky Way would become a furnace of stellar birth. These new stars, massive and blue-white in color, would burn with a furious intensity. Their lifespans are measured not in billions of years like our sun, but in mere millions. They would be giants in the cosmic sense, some of them burning 100 times brighter than Sol. And because they are so massive, they would burn their hydrogen so quickly that they would exhaust their fuel almost before the collision had fully progressed. They would explode, they would die, and in dying, they would seed the surrounding gas with the heavy elements necessary for rocky planets, and eventually, life as we know it. The cruelty and beauty of it might give you pause. A galactic collision, for all its chaos, would be a generator of creation, a destroyer that builds. The visual spectacle of this moment, were one somehow able to observe it, and this is where we step more fully into speculation, though the principle is grounded in real astronomy, would be extraordinary. Imagine the night sky filled not with the steady glow of ancient stars, but with waves of new brightness, propagating outward from the regions of greatest compression. The bridges of tidal tails that stretch between the two galaxies would light up like capillaries filling with blood. The warped spiral arms would develop a marbled appearance, regions of incandescent blue where the new stars burn brightest, interspersed with dark lanes of dust that the radiation has not yet pierced. These bright nurseries would not persist indefinitely, of course. The massive stars would age and perish within a few million years. But their deaths would trigger further compressions in the surrounding clouds, further births, further deaths. The collision would set off a cascade of star formation that could continue for hundreds of millions of years, a cosmically extended period of extreme fertility born from chaos. In this sense, the merger of the Milky Way and Andromeda would not be purely destructive. It would be generative, wasteful, perhaps, disruptive, certainly, but also alive in a way that two separate, serene galaxies drifting through the void would never quite be. And yet, in all of this cosmic activity, all of this birth and death and light and shadow, the vast majority of space would remain empty. Between the new star clusters, between the clouds of gas being stirred and compressed, would still be nothing but vacuum. The collision would be fierce by the standards of galaxies, but it would still be, fundamentally, a collision between two nearly empty spaces. This is the paradox that underlies all of cosmology. The universe appears full of light and matter until you truly contemplate its scale, at which point you realize it is emptiness dotted with islands of activity. Even a galactic collision is, in a sense, a gentle affair. Even the fury of two spirals colliding and merging would leave most of the cosmos indifferent. The new stars, those frantic blue children of compression, would scatter throughout the disturbed arms of both galaxies. Some would form in clusters, their gravity holding them loosely together, at least for a time. Others would emerge in isolation, surrounded by the dust and gas from which they had just coalesced. And all of them would be part of a single, unified process, the reshaping of the cosmos itself, one stellar nursery at a time. And now, as those tidal forces begin their work on both spirals, pulling and stretching and drawing new stars from their ancient rest, a peculiar and perhaps strangely comforting thing would unfold for us here on Earth. The chaos we have been imagining, all those turbulent streams of gas and the new stars being born in compressed clouds, would continue around us, vast and terrible and beautiful, while our own corner of space remained largely untouched. This is not luck, precisely, though it may feel that way. It is simply the mathematics of cosmic distance asserting itself even as everything appears to be falling inward. Consider the Oort cloud, that distant halo of dormant comets that marks the true boundary of our solar system's influence. It extends outward to perhaps 100,000 times the distance from Earth to the Sun, creating an enormous sphere of gravitational possession around our star. Andromeda's approach would be violent on galactic scales, yes, but the collision itself would unfold across millions of years. Our compressed thought experiment has stripped away that buffer of time. Even so, in our imagined tomorrow scenario, Andromeda would need to pass quite close to us in the densest parts of its core to begin disrupting these outer reaches. The odds of our system being in the direct path of Andromeda's nucleus are extraordinarily small, like calculating the probability that two people, walking across entire continents, would happen to collide at precisely the same moment. The real question worth sitting with as you drift here is this: what would have to happen for Earth itself to be displaced? The gravitational pull from passing stars, even the nearest ones in Andromeda's tide-torn arms, would be measurable. Astronomers could detect it, calculate it, model it with precision, but measurable does not mean destructive. A star would need to approach within a few light years of Earth's position to begin tugging us away from the Sun with any real force. A few light years. In the compressed moment of this collision, the vast majority of Andromeda's stars would sail past at distances measured in thousands of light years, even as the two galaxies merged their structures around them. The intergalactic space is so impossibly large that even when two galaxies appear to collide in our sky, their individual stars pass through the voids between them like ghosts passing through walls. There is a meditation hiding in this fact, one worth letting settle into the quiet of your mind. Within the grand upheaval of a galactic merger, with gas clouds igniting and spiral arms unwinding, and the shapes of both galaxies distorting beyond recognition, the zone of true stillness, the region where the Sun would continue its patient fusion and Earth would continue its orbit, would be almost criminally peaceful. The Sun's gravity, that faithful anchor that has held our planet for 4.5 billion years, would remain the dominant force in our immediate neighborhood. The Sun's gravity cares nothing for what happens 1,000 light years away. It cares only for what is near, and we are its nearest possession. There is another layer to this safety that emerges from the very nature of galactic structure itself. Both the Milky Way and Andromeda contain not just stars, but enormous regions of near-perfect emptiness. The stars that fill them are so far apart, relatively speaking, that two passing through each other is not like two buildings colliding, but more like two vast clouds of smoke passing through each other on a still night. If you took a scale model of the solar system, one where the Sun was the size of a marble on a football field, a nearby star would be a marble on another football field several miles away. Now multiply that distance by a factor that makes your mind feel small. That is the true scale of stellar spacing. Earth's future would not be determined by the cosmic drama playing out around us, but by the intimate and local gravity well of the Sun. What would change in our skies, though, and this is worth imagining as you rest with your eyes closed, the constellations would begin a slow, gradual transformation. As stars from Andromeda's arms drifted through the greater Milky Way region over millions of years following the collision, the familiar patterns that humans have named and followed would slowly shift. Orion would not disappear overnight. Ursa Major would not suddenly vanish from its place. But over the lifetimes of countless human generations, the slow waltz of stellar positions would become apparent. The night sky your great-great-great-grandchildren would see would be a different tapestry than the one you know now, a subtle change, like watching a tapestry very slowly reweave itself under the hands of an invisible artist. But in the immediate aftermath of this imagined tomorrow collision, in those first thousands of years, which is barely a blink on cosmic timescales, Earth would orbit as it always has. The Sun would fuse hydrogen into helium, as it has been doing for billions of years. The Van Allen belts would continue their spiraling dance around our magnetic poles. The Moon would continue its slow retreat from us, moving away at about the width of a fingernail each year. Life, if it had survived the chaos of the merger, and there is genuine uncertainty here, for the increased radiation from all those new stellar births and gravitational disruptions might have posed challenges to atmosphere and biosphere. Life could continue its ancient unfolding, indifferent to the transformation happening in the larger cosmos around it. This is perhaps the deepest comfort one can draw from contemplating such vast scales. Even in the collision between two galaxies, the personal and the intimate remain protected. The bubble of warmth around a small star in the suburbs of a spiral disk continues to hold. We are so small and yet so held. At the heart of each galaxy lies a monster, though the word itself seems too crude for something so strange and patient. In the center of our Milky Way, some 26,000 light-years distant from where Earth spins in its quiet orbit, there exists a region of space so dense, so fundamentally twisted by gravity, that not even light escapes its pull. We call it Sagittarius A star, and its mass is 4 million times that of our Sun, compressed into a space smaller than the orbit of Mercury. It does not roam, it simply sits, a singular point of no return, drawing the orbits of ancient stars around itself in elaborate, century-spanning dances that astronomers have learned to measure with exquisite precision. In Andromeda, 2.5 million light-years away from our vantage point, there exists another such creature. Its black hole is perhaps as much as 100 million times the mass of our Sun, a thing so vast that it dwarfs Sagittarius A star in comparison. And yet, in the tomorrow that is not, when Andromeda's galactic disk begins its slow, irresistible fall toward our own, these two monsters would eventually find themselves drawn toward each other by the very force that commands all movement in the cosmos. Gravity does not tire, it does not negotiate, it simply pulls, infinitely patient, across any distance that matter or energy permits. For a very long time, and when we speak of cosmic time, we measure in hundreds of millions of years, each one a million millennia by the reckoning of human history. These two black holes would orbit around a common center of mass, their gravitational fields locked in a dance that would be nearly invisible to any observer watching from afar. The stars around them would swirl and settle into new configurations. The gas clouds would gradually be stripped away or consumed, but the 2 points of infinite darkness at the galactic cores would remain, circling each other, their paths growing gradually, imperceptibly tighter, with each passing million-year waltz around their invisible center. How do two objects locked in mutual gravity grow closer when they are already orbiting one another? The answer lies in something that Einstein could never quite hold in his hands, something that the detectors of Earth have only recently learned to listen for: gravitational waves. As the black holes orbit, the very fabric of space and time around them begins to ripple, vibrating like the surface of a plucked string, though the plucking happens on a scale of light years and the vibrations travel outward at the speed of light itself. With each wobble in the cosmos, each undulation of space-time, a tiny amount of orbital energy radiates away into the void. And as that energy leaves, the two black holes spiral closer, their orbit accelerating, their period shortening from millions of years to thousands, then hundreds, then months. In our scenario, of course, all of this would happen in perhaps 1 billion years or so, a time span that feels like forever to any creature that thinks and breathes and measures its own life in decades. But by the standards of stars and galaxies, it is a blink. It is the space between one cosmic age and another, and so the merger would come, inevitable as the seasons, but stretched across a timeline so vast that no human civilization would ever witness it, no matter how our species might evolve or persist. In those final moments before the merger, the two black holes would be invisible to any telescope, yet their presence would be undeniable, written into the motion of stars circling around empty space, drawn into intricate formations by the gravitational whip of something that cannot be seen, but only felt. The region around them would grow hot with friction. Gas and dust, drawn inward by both black holes' immense pull, would heat to temperatures that make the cores of stars seem cool and pleasant by comparison. X-rays would pour out in torrents that we would recognize from light years away, a beacon announcing the approaching marriage of these two impossible objects. And then, in the final seconds before contact, something remarkable would occur. The gravitational waves would swell from whispers to roars, rippling outward through the entire expanding cloud of merging matter. The very universe would ring with the impact, a vibration so profound that sensitive instruments on distant worlds, if such worlds existed and such beings had the wisdom to build such instruments, would shudder and sing in response. Two singularities, two infinities, would touch and merge into one larger infinity, and the geometry of space around that point would undergo a transformation for which mathematics still strains to find adequate language. The supermassive black holes at the heart of Andromeda and the Milky Way, then, would not collide in the violent, explosive way that our tomorrow scenario might lead us to imagine. Instead, they would conduct a slow, inexorable courtship across the better part of 1 billion years, guided by forces that act on scales so large and with such patience that human patience itself becomes a joke, a failure of imagination. They would spiral ever closer, visible only through their effects on the matter around them, until at last they would merge into a single, even more massive black hole, the heart of what would become, at last, a single elliptical galaxy. And the universe, in its vast indifference and its fundamental unity, would have orchestrated one of the most dramatic transformations a cosmos can manage, without a single star needing to move more than a few 100,000 miles from its current position. At the heart of our galaxy spins Sagittarius A, a supermassive black hole so massive that 4 million suns could fit inside its event horizon. For billions of years, it has orbited quietly at the center of the Milky Way, anchoring the entire spiral with its gravity, holding vast clouds of gas and dust in their slow, eternal dance. And at the heart of Andromeda, equally ancient and equally patient, waits its own supermassive black hole, perhaps slightly larger still, a gravitational anchor for 100 billion stars. When two galaxies merge, truly merge, not merely brush past each other, their central black holes do not immediately collide. Instead, they begin a cosmic waltz that unfolds across millions of years. As the galactic cores approach and spiral inward, the black holes themselves enter into a gravitational embrace so profound that it reshapes space-time itself around them. They begin to orbit each other in ever-tightening spirals, their paths converging not by accident, but by the geometry of curved space-time, the very fabric that Einstein described more than a century ago. The fascinating question that emerges in these final stages is whether the two black holes will ever truly merge at all. For millions of years, as our imagined collision takes its course, they orbit and orbit, drawing closer by fractions of a light year with each revolution. But there exists a curious threshold called the final parsec problem, a puzzle that has occupied astronomers and theoreticians for decades. At a certain distance, roughly 1 parsec, or about 3.2 light-years apart, the black holes may struggle to close that final gap. Why? Because the surrounding stars and stellar remnants, flung outward by the merger of the two galaxies, continue to exert subtle gravitational tugs on both black holes. These tugs can actually slow their inward spiral, creating a strange cosmic stalemate, where the black holes orbit each other for an enormously long time without finally merging. It is as if the universe itself keeps them suspended in an elaborate cosmic dance, neither able to fully commit to union. Yet newer simulations and observations suggest that this problem may not be insurmountable. Eventually, through the loss of energy and momentum to these surrounding stellar remnants, the two black holes do continue their descent. And as they spiral closer, as they truly draw near in the final moments before merger, something remarkable begins to happen. The motion itself becomes so violent, so energetically intense that it tears at the fabric of space-time itself. In 2015, instruments called LIGO detected something that had never been directly observed before: gravitational waves. These are ripples in space-time itself, emanating from the collision of two distant black holes, each roughly 30 times the mass of our Sun. The waves propagated outward at the speed of light, reaching Earth as the tiniest tremor, detectable only by the most sensitive instruments humanity has ever created. The black holes at the heart of our merging galaxies would emit gravitational waves far more powerful, far more dramatic than anything LIGO has yet recorded. As Sagittarius A and Andromeda's black holes spiral closer in their final million years, their final 1,000 years, their orbital velocity increases to a significant fraction of the speed of light. The sheer energy released in the form of gravitational waves becomes staggering, almost unimaginable. These waves ripple outward through the universe, carrying away energy with such efficiency that the black holes accelerate their inward spiral. It becomes a runaway process, a positive feedback loop where the very act of radiating energy in the form of gravitational waves pulls them closer, makes them spin faster, radiates more waves still. The final moments would be almost absurdly brief by cosmic standards. In the last seconds before merger, the two black holes would be circling each other thousands of times per second, their surfaces nearly touching in a frantic, violent ballet. The gravitational waves would reach a crescendo of intensity. The space-time curvature around them would become so extreme that observational reality itself would strain under the weight of physics being pushed to its limits. And then, in what would be experienced as an instant at the cosmic scale, they would merge. The event horizons would touch, then merge into one. Two immense gravitational wells would become a single, larger well. In that moment of union, the peak energy output would exceed the power radiated by all the stars in the observable universe combined, released entirely in the form of gravitational waves. And then, almost as suddenly, it would be over. The waves would propagate outward at light speed, and the newborn, merged black hole would begin to ring like a bell struck in the cosmic dark, its vibrations slowly damping over time. This merged black hole would be heavier than either predecessor, its event horizon larger, its gravity reshaping the very center of what would now be Milky. It would sit at the heart of the new elliptical galaxy, waiting in its quiet singularity, as it has always waited and always will. And so, millions of years into this grand collision, something remarkable would emerge from the chaos. The two galaxies, which had spent such a long time as distinct island universes, separated by the void, would finally settle into a single, unified structure. Astronomers call this merged form Milky, though no human eye will ever witness its completion. We exist in a moment too early, and those who come after will arrive too late to see the moment of final union. What Milky would be, in its completed state, is something entirely different from either parent galaxy. Where the Milky Way spirals with elegant arms of dust and gas, and where Andromeda swirls in her own grand design, their offspring would be an elliptical galaxy, not a spiral, not a disk, but a vast rounded halo of ancient stars, stretched and pulled and reformed into a shape almost featureless by human standards, yet profound in its own quiet way. The spiraling arms would be gone. The dust lanes that once sketched galactic architecture across the darkness would be largely consumed, either pulled into the gravitational furnace at the core or flung outward into a diffuse halo extending impossibly far into space. Picture, if you can imagine it, a night sky billions of years hence. If some distant observer were to stand on a planet, orbiting one of the surviving suns, perhaps Earth itself, if its orbit remains stable enough to permit life through all these transformations, the constellations they know would be utterly unrecognizable. The Milky Way, that familiar clouded river that has inspired myth and navigation and wonder for all of human history, would no longer exist as a stripe across the heavens. Instead, there would be a single, vast, luminous halo, perhaps stretching across a significant portion of the sky, a gentle glow of trillions of ancient, cool stars. Red dwarfs, primarily, the longest-lived stars in the universe, burning slowly and steadily. The galactic core would be visible, not as a distant bulge in one direction, but perhaps more centrally positioned from certain vantage points, and the surrounding stars would thin gradually toward the periphery rather than arrayed in those graceful spiral arms. The night sky itself would feel different. There would be less dust between observers and the distant stars, which might seem counterintuitive given the chaos of the collision, but the violent interaction would have cleared much of the remaining gas into the intergalactic medium. The sky would perhaps appear clearer, colder, more austere. Background galaxies, those faint and distant universes beyond the Milky Way that we can only detect with instruments today, might appear more numerous, less obscured by the dust clouds that currently veil them. Andromeda, or rather what remains recognizable as Andromeda, would be indistinguishable from the rest of the galactic structure. There would be no Andromeda anymore. There would be only Milkomeda, and the stars that comprise two distinct galactic histories would have become one continuous, unified system. The great supermassive black holes, Sagittarius A, and its Andromedan counterpart, would by this point have completed their merger. Somewhere near the heart of Milkomeda, a single black hole of almost incomprehensible mass would rest, perhaps still settling, perhaps still emitting those gravitational whispers detected as faint radiation ripples in the fabric of space-time itself. The region around this core would be violent in its own way, a dense, ancient population of stars orbiting in chaotic patterns, occasional stars drawn too close to the event horizon and torn apart, their matter spiraling inward in brilliant, brief cascades of light. And yet, for all this transformation, the universe would barely register the change. Those future observers, should they exist, might look outward from their world and wonder whether the shape of their home galaxy was always this way, or whether something profound had occurred in the deep past. The timescales involved are so vast that written record would be utterly impossible. The rise and fall of civilizations would be dust on dust. Species would evolve and vanish. Continents would move. The very chemistry of planets would shift and alter. And through it all, the stars would continue their patient burning, the slow fusion reactions converting hydrogen to helium, second by second, year by year, age by age. This is the nature of galactic transformation. It is not violent in the way that human catastrophe is violent. It is not quick, and therefore it does not feel urgent. A star that survives the collision, and most would, might orbit for billions of years after the merger is complete, before ever feeling any significant gravitational disturbance. The timescales are so immense that they seem almost peaceful, almost gentle, despite the tremendous forces at work. Two galaxies, each containing billions of stars, each containing the potential for billions of worlds, merging into one, and in the compressed telescopic view of a documentary, in the gentle narration of someone guiding you towards sleep, it feels like watching dust settle in moonlight, inevitable, quiet, almost serene. The future night sky under Milkomeda would be, paradoxically, both less alien and more profound than our current view. Less alien because the fundamental physics would be unchanged. Stars would still burn, planets would still orbit. Life, if it persisted, would still wonder at the heavens above. More profound because it would be a sight no earth-born creature could imagine in detail, a transformation that would erase billions of years of cosmic history and write a new chapter in the stellar record. The memory of two distinct galaxies, separated by void and distance, would exist only in the data that astronomers today laboriously preserve, in the photographs and measurements that suggest to us, across the gulf of time, that such a thing once was. And so we return, at last, to the simplest truth. 4 billion years is not a number that fits inside a human life. We measure our days in sunrises and seasons, in the turning of years and the slow accumulation of memory. 4 billion years is the time it takes for continents to drift, for species to bloom and vanish without trace, for mountains to crumble into soil. It is longer than the entire span of complex life on Earth. It is, in any meaningful sense, forever. Yet here we sit, on a small rocky world orbiting an ordinary star in an ordinary suburb of an ordinary spiral galaxy, knowing that this collision is coming. We know it as surely as we know that the sun will set tomorrow, even though tomorrow is eons away. There is something both humbling and strangely comforting in that knowledge, is there not? We are small. Our concerns, our ambitions, our fleeting moments of joy and sorrow, they occupy a space so infinitesimal against the backdrop of cosmic time that they might seem to vanish entirely. And yet, it is precisely because we are small that we are here at all. The atoms that make up your body were forged in the heart of stars that died long before our sun was born. The calcium in your bones, the iron in your blood, the oxygen in every breath you draw, these are the gifts of stellar furnaces, the legacy of supernovae that exploded when the galaxy was young. You are made of stardust, not as poetry, but as literal, measurable fact. And that stardust has been recycled countless times, passed from star to star, woven into planets, incorporated into the chemistry of life itself. When Andromeda's gravity begins to pull at our galaxy in earnest, not tomorrow, but in the patient, inexorable march of 4 billion years, your descendants will look up at a sky transformed. The modest smudge of Andromeda will have swollen to fill a quarter of the heavens. The spiral arms of both galaxies will have been drawn out into graceful streams. New stars will be igniting in the compressed gas clouds, brilliant nurseries scattered across that transformed sky. And if consciousness persists in any form by then, if thinking beings still exist to witness it, they will see something that no human eye has ever seen. They will see the birth of Milky, the slow marriage of two galaxies becoming one. But you will not see this. Your children will not see it, nor their children, nor anyone born for 10,000 generations to come. There will be countless dawns between now and then, countless turnings of the seasons, countless moments of beauty and connection and meaning. There will be discoveries that reshape our understanding of reality. There will be love and loss, triumph and sorrow, the ordinary, extraordinary texture of existence played out against a stable sky. For now, for your lifetime, and for many lifetimes beyond, the night sky remains recognizable. Andromeda still appears as it has for all of recorded human history, a faint smudge of light in the autumn and winter sky, an island universe so distant that its true nature was only confirmed within the last century. The constellations that your ancestors traced remain largely unchanged. Orion still hunts across the winter heavens. The Pleiades still dance their ancient dance. The familiar and the stable still hold their ground. This is perhaps the deepest comfort in contemplating such vast timescales. The universe is indifferent to us, yes. Our individual lives are negligible against the sweep of cosmic history. But we are not insignificant in the sense of being meaningless. We are significant precisely because we are conscious. We are the universe becoming aware of itself. We are the way that these stars that died to create us now look back and comprehend their own origins. Through us, through human curiosity and wonder, and the slow, patient work of understanding, the cosmos knows itself. And so beneath the sky, that is still ours for now, that has looked down on every moment of human hope and suffering and joy, that has ever occurred, we can rest easy. The collision is coming, yes, but it is coming in a time frame so vast that it dissolves into irrelevance against the backdrop of any individual human concern. We are held, for now, in a moment of cosmic stability. We are given time, vast amounts of time, to learn, to grow, to love, to wonder. When you drift off to sleep tonight, the sky outside your window is the same sky that looked down on every civilization that has ever risen and fallen on this world. The same constellations that guided ancient sailors guide us still. The light from Andromeda that reaches your eye tonight has been traveling for 2.5 million years, carrying with it the image of a galaxy that will not collide with ours for 4 billion years more. That light crossed the vast emptiness of intergalactic space just to reach your small and temporary form, and in that reaching, creates a connection that spans both time and distance. The stars are patient. The universe operates on timescales that dwarf human understanding, yet we are part of it. We belong to it as completely as any star, or galaxy, or speck of cosmic dust. We are woven from its fabric. Our consciousness is its greatest achievement, at least as far as we know. And so we can rest, knowing that we are held in a cosmos far grander and stranger and more wondrous than we can fully comprehend, yet a cosmos that is, in its deep structure, our home. The night sky will be there when you wake. Andromeda will still be there, patient and distant, beginning its imperceptible approach. The collision that would reshape the entire galaxy is proceeding right now, too slowly for any instrument to measure in real time, too distant to concern us in any practical way. And we are here, briefly, impossibly fortunate to exist in this moment of stability and wonder. Let that knowledge settle into your mind as your breathing slows. You are part of something infinite. You belong to a universe of such grandeur that it can barely be grasped. And for now, the sky is still, the night is quiet, and you are safe beneath the light of stars that will shine on long after you have gone.